Right, grade 12s, now we move on to section 3.2, which is the second part of topic 3, derivatives of exponentials and logs, and this is the log function part. And I love the derivative of ln x. We only really do logs with the base of e in AP Maths, so we're only going to differentiate ln x, and the derivative of ln x is 1 over x. Now, why does it say for x is greater than 0? Logs are only defined when x is greater than 0, simply because you can't log a negative. An answer can never be negative for an exponential function. So why is it easy to prove that that derivative is 1 over x? Well, first of all, let's have a look at the fact that if we make y equal to ln x, that means y equals log base e of x. So if we rearranged it, that means that e to the power of y equals x. Now what that means is that you've isolated x. So if we were going to differentiate, you would be differentiating x with respect to y, which is quite a weird thing for us, but you can differentiate anything with respect to something. So here we've isolated x, so we're going to differentiate what x is equal to with respect to y. Now we've just done the fact that the derivative of e to the power of something is just e to the power of something. So it's that simple. Now, what we're going to do next is we want dy dx. So I'm going to swap these around. So this is making this dy dx, which I know that I can do as long as I swap this fraction around. So it's 1 over e to the y. Now, hang on, wait one moment. E to the y means that this is e to the power of, and y was ln x. Now, I'm not too sure if you remember when we did exponential exponents and logs, and we did the log laws. We learnt a log law that said if you have any base, if you have a base of a to the power of log base a of x, that answer is simply x. So I don't know if you remember doing that log law when we did log laws, but as long as, if this is your base and you raise it to log the power of a base of x, now we did prove that at the time, so it's just page back in your book and see, because it was quite a nifty proof. But that means that this derivative with respect to x is actually just going to be 1 over x, which is really, really cool. So the derivative of ln x is 1 over x. So let's have a look. Since that's quite easy, what type of questions can they ask? Well, if they say to you that y is equal to negative 3x ln x, this is a product, because there is function number 1, and here is function number 2, which means we need to use the product rule. So either I could say y dashed or dy dx. I'm going to say y dashed. Now, let's just remember the product rule. The product rule said differentiate the first, which is minus 3, leave the second alone, so that is ln x, and then plus leave the first, which is minus 3x, and differentiate the second. Now the derivative of ln x is 1 over x. Sorry, let me get my color right. Is 1 over x. This is times 1 over x. So I can definitely neaten this up. So if I neaten this up, this is negative 3 ln x, and then the x's will cancel, so I just get minus 3. So that's really cool. So that was the product rule, but also using ln x. Okay, let's look at question B. Now question B is a chain function. Now why this is a chain rule type of question, I shouldn't say chain function, this is a function that needs the chain rule, is that this is ln of something. So I have an outside function, which is the ln. So my outside function is the fact that it's ln something. And then I've got an inside function, which in this case is 3 plus 2x squared. So ln of x is 1 over x, but the moment I make that inside just a little bit more interesting, then it's an inside function. So y dash should be, now we're going to use our chain rule. Our chain rule says that differentiate the outside function. Now the outside function is ln of something, and ln of something differentiates to 1 over that something. So it's 1 over 3 plus 2x squared, and then I need to multiply by the derivative of the inside function, because that's what the chain rule says. Differentiate the outside multiplied by differentiate the inside, and this inside function differentiates to 4x. So we actually end up getting, if I just write this a little bit more neatly, we'll end up getting 4x over 3 plus 2x squared. Now what this actually means is what I've put in a box. If you have f of x which is ln of a function, so not just x, something a little bit more interesting, so ln g of x, then the derivative is 1 over g of x, because that's the outside function, that's the ln idea, 1 over the function inside the ln, multiplied by the derivative of that inside function. So you basically land up with g dashed x over g of x, lands up being your rule. Now I don't actually use that rule every time, I just think of the chain rule in my head, but it does make sense. Okay, let's do loads of examples now. Differentiate the following. Ln of 4x. Well, that's a chain rule, because 4x is the inside function, so the outside function means I do 1 over 4x, but then I need to multiply by the derivative of the inside function, which is 4x, so the derivative is 4. So I actually land up with y dashed in this case being 1 over x. So that was a chain rule. Okay, next one, also a chain rule. The inside function is equal to this mess here. So the outside function is ln, so it's 1 over 4x cubed plus 3x plus 9, multiplied by the derivative of the inside function, which is 12x squared plus 3. So that's exactly what we were saying in the rule. It's the derivative of the inside function over the inside function. Now I can't simplify that at all, but it's really cool. Okay, let's look at the next one. Now this one's a little bit tricky, simply because you have to understand what it's saying. This is not the same thing as me saying ln of x squared minus 4x cubed. I'm not cubing the whole thing, because then the cube would have to be in a big bracket around the ln. What am I cubing? I'm cubing that. Now this means that this is going to be a chain rule within a chain rule, because your outside function will be your ln. There's your outside function, and my inside function will be this x squared minus 4x all raised to the power of 3. But because that's a chain rule within itself, multiplying by that derivative gets a bit messy. Now it's not doable, it's just a bit messy. So the question is, can we always keep in mind our log laws to make our lives easier? So I'm just going to write myself a note here. Keep in mind the log laws, because the log laws, because they make your lives easier. So what log law am I talking about here? Here I'm talking about the log law that said if you have ln, so ln a to the power of n equals n ln a. That whole bringing down the exponent law. So always keep in mind that exponent laws can help you. So here, for example, would it not be more beneficial for us to bring down that 3 to avoid the chain rule later? So this is 3 ln x squared minus 4x. It completely destroys the need for the chain rule within that inside function, and that 3 in front is simply a coefficient, so it really plays no role here. So now this is my only inside function, and I've got f dashed x will be equal to 3, which has to be there. Now ln of something differentiates to over x squared minus 4x. Sorry, that doesn't look like a squared. And then I'd need to multiply by the derivative of the inside function, which will be 2x minus 4. So if I just make that a little bit neater, so this is 6x minus 12 over x squared minus 4x. Much easier than thinking of that inside function as a chain rule within itself. Now what's quite interesting is if we did that inside function as a chain rule within inside itself, you might get something that looks slightly different. And so never think that you've done something wrong if you check the memo and your derivative doesn't look exactly the same. It's weird depending on different methods you take. You can get very different looking answers. The fact is always that they are equivalent. Right, let's look at the next question, D. And once again, let's just keep in mind that sometimes the log laws can help us. So let's have a look here. We have ln, and then we have an inside function. So by definition of the fact that this is a ln of a function, this is immediately a chain rule. Unfortunately, inside is going to be another chain rule, because that's a root, which is an exponent of a half, and then inside that I have a function. So this is going to be another chain rule within a chain rule. And so if I ever have a chain rule within a chain rule, I need to start thinking, is there a way I can get around that by using a log law? And this is exactly the same concept as the previous question. Can I bring down the exponents of a half? And therefore, I am destroying one of the chain rules that I need, because I've taken that exponent, which makes it a chain rule, and brought it down to be a coefficient. So now, my outside function is the idea of ln, and my inside function is this x squared minus 1. So finally, I can say g dash x. Remember, the half is just a coefficient, so it stays around, so it's a half, multiplied by the derivative of ln is 1 over whatever you are linning, if that's a word, and the derivative of the inside function is 2x. And now I can do a little bit of simplifying here, because my 2 on the top and 2 on the bottom can cancel, and so I get x over x squared minus 1. So again, another log law helping us out there. Right, going down to e. Now this is fairly complicated. I'm afraid it isn't written very easily, because you kind of wonder, is that x cubed, or was that a cube root of? Now sorry, that was meant to be a cube root of, so this is meant to look like the fact that you are linning x multiplied by the cube root of x squared plus 4. So I am taking the log of the ln of that, and so immediately I'm like, cool, this is a chain rule, because whatever I'm logging I will need to differentiate. The only problem is this is horrible. This inside here is absolutely horrible, because that would be a product, and within that product, that second function, which is going to be this thing, that's going to be a chain. So basically, the fact that we have ln is going to cause a chain, and then inside we're going to have a product that has its own chain. I mean, that's even worse than C and D. So again, we say to ourselves, are there any log laws that can help us? The moment it's going to be completely crazy. What log laws could simplify this for us? Now, I'm not too sure if you remember that ln of A times B, if you have a product within a log, it's the sum of the individual logs. So that was one of the first log laws that we did. And so really nifty here, we can change y. This is going to be ln of the first function plus ln of the second function. And immediately I'm going to change that second function to a root. To an exponent as opposed to a root, simply because then I can do exactly what I was doing in C and D, and I can bring down that exponent as a coefficient, and then that destroys the need for a chain within a chain. So that's pretty nifty. There were two log laws going on there, the product log law and the whole power log law. And now I'm ready to differentiate. So you can call it dy dx or y dashed. Now the derivative of ln x is just 1 over x. That's not a chain rule. You could think of it as a chain rule, because it's 1 over x times the derivative of the inside, and the derivative of x is 1. And so it's kind of pointless. And then the next one is a third multiplied by, and I'll have to go 1 over x squared plus 4, and then times the derivative of the inside function. So remember, it's 1 over whatever's inside the ln, and then times the derivative of the inside. And so I can write that a little bit more neatly, because I can just say it's 2x at the top over 3x squared plus 4. And I wouldn't bother, LC doing that or anything. I would leave it like it is. So really cool question where the log laws are helping us with our differentiation. Excellent. Now, this again is going to be a nifty log law one, because the moment I see that, I'm like, this is disgustingly horrible. I mean, that's a quotient, and within that quotient you have a chain. So by the fact that you have a log here, that's going to make this a chain rule. Then you have a quotient, and within the quotient you have a chain rule. That's terrible. So once again we say to ourselves, do we have a log law that will help us out? And we do, because we have the quotient log law. The quotient log law says that if you are logging a quotient, it's the same as logging them individually and subtracting. So I'm going to change this to the ln of, and I'm going to change x plus 4 square rooted to an exponent of a half, simply so that I can bring down that exponent and use my next log law. So that's my first log law that will help me. My second log law is going to be this. bring down the exponent of a half, bring down that exponent of 3, so this is no longer a chain rule within a chain rule. Now I think I'm ready to differentiate, so y dashed, remember the half is just a coefficient, times, and it's 1 over whatever you are logging, multiplied by the derivative of the inside, which is 1, minus 3 times 1 over whatever you are logging, multiplied by the derivative of the inside function, which is 4. So if I neaten that up, I get 1 over, and you can write this as 2x plus 8, but you can leave it as unmultiplied out, and this is minus 12 over 4x minus 1. So that one's pretty cool. And the next one looks fairly similar. Looks like we're practicing the same idea. So this again is a quotient, so I'm going to use the quotient log law. So I'm going to say, right, we're logging, and this is x plus 1 to the power of a third minus the ln of 4 minus x. Now I'm going to bring down the third so that I can not make this a chain within a chain. And now finally I'm ready to differentiate. And so in order to differentiate, y dashed, the third is just the coefficient. It's 1 over x plus 1 times the derivative of the inside, which is 1, and then minus 1 over 4 minus x times the derivative of the inside, which is actually negative 1. So this, written more simply, is 1 over 3x plus 1, and this is just plus 1 over 4 minus x. So really, really nifty how the log laws can help us. I really love these log law derivatives. They're really quite fun. Right, let's soldier on. We've got some more to do. F of x equals x squared ln x cubed. Now again, that's not ln x altogether cubed, it's x cubed. So the moment I see this, I'm thinking product. Definitely. I mean, those are two separate functions. There's no log law. I can't bring down the 3 here. I suppose I could bring down the 3. I just thought about that. Why do I want to bring down the 3? So I'm saying f dashed x. This is not f dashed x. I was just thinking ln of x cubed is the same thing as 3 ln x. And I do actually want to do that because what it does is it destroys again that need for the chain within the chain. So first steps first, I would bring down the 3, which actually means that that 3 can go to the front almost as just a coefficient because it does, remember, multiplication is commutative, so I can put it at the front. So again, this is still a product. We still haven't destroyed the fact that this is a product, but I can actually think of that as function number 1 if you want. It doesn't really matter where that 3 is, and that is function number 2. And so what did the product rule say to us? The product rule says, now remember to talk yourself through it, the product rule said differentiate the first function, which would now be 6x, leave the second function alone. So times ln x plus leave the first function alone, which would be 3x squared, times the derivative of the second function, which would now be 1 over x. So if I write that a little bit more neatly, I'd get 6x ln x, and one of my x's would cancel, so I get plus 3x. So that's pretty nifty. Again, the log law helping me, but that was a log law and then a product. Now, just out of interest, let's try and do this question if we didn't use the log law and see what we'd get. So if we didn't use the log law, we would have said f dash, sorry, not f dash, let's write out f of x. F of x equals x squared times ln x cubed. And this would be function number 1, and this would be function number 2. And so the product rule would have said to us, differentiate the first function, which would have been 2x, leave the second function alone, which was ln x cubed, plus leave the first function, x squared, times the derivative of the second function. Now this would be 1 over x cubed, but then I'd have to multiply by the derivative of the inside, which is x cubed. I suppose that's not actually too bad because it doesn't become a chain within a chain too much, so that's times 3x squared. So this actually isn't too bad. let's neaten it up. So I get 2x times ln x cubed plus, now I've got x squared times 3 times x squared, so that'll be 3x to the power of 4, but over x cubed, so plus 3x. Now, those don't look alike. Now, the only reason they don't look alike is that this one has now brought down the 3 using the log law, and I actually get the same answer. So the reason why this wasn't actually too much more difficult is that this actually, I said earlier that this was a chain within a chain, but it actually isn't, only because that's x cubed. If that was something like, I don't know, x squared plus 1 cubed, then it would be quite a mission, because differentiating that would be a chain within a chain. But it actually wasn't, so that was pretty nifty. And ultimately, if you hadn't done this line, but had left it there, you would get the right answer. I mean, there's nothing wrong with that as a simplified answer. So that was pretty cool. Right, on to I. Ln of e to the x times e to the x minus 1. Now, that's a bit weird. I mean, I suppose there's multiple ways to do this. One of the ways to do this would be to multiply this out. I mean, that was my first instinct. My first instinct was to say, well, let's multiply that out. Then that's e to the 2x minus e to the x. Okay, another way to do this as I was looking at it is thinking of this as logging a product. So this is ln A, B, you know, those are A and B there. So I could then see it as ln e to the x plus ln e to the x minus 1. So those are both perfectly acceptable ways to do it. If we did it the first way, I could now find dy dx, or y dashed, because I would have to say it's 1 over e to the 2x minus e to the x, and then multiply by the derivative of the inside. Now the inside is this. Now e to the 2x would differentiate to e to the 2x, but multiplied by 2, because that's a chain rule within itself. Remember, it's e to the 2x, but the inside function is 2x, and e to the x is just e to the x. So that would be my y dash the first way. If I write this out a little bit better, this is 2e to the x minus e to the x all over e to the 2x minus e to the x. Now that looks weirdly kind of simplifiable some more, and so I'm pretty sure I could possibly take out an e to the x as a common factor. If I took out e to the x as a common factor at the top, I'd get 2e to the x, because remember, when you multiply powers the same base, I would have added those exponents. I would have got e to the 2x, and then minus 1, and if I take out an e to the x at the bottom, I would have e to the x minus 1. And so I can actually land up cancelling those off and getting just this as my answer. Now let's see, if we did it the other way, what answer would we get, and how similar would they look, if not identical? Obviously, they always have to be equivalent, but they don't have to look identical. So ln of e to the power of x. So if I differentiate that, right, I would get 1 over e to the x. So because I'm linning e to the x, I'd get 1 over e to the x times by the derivative of the inside function, which is e to the x. So I'm just thinking, which is e to the x. So e to the x differentiates to e to the x. Okay, so 1 over e to the x, which is the outside function, that's the ln, times the derivative of the inside, which is e to the x, plus, again, this is the same idea, 1 over e to the x minus 1, because it's ln, but then you need to multiply by the derivative of the inside function, and the derivative of e to the x is e to the x, and the derivative of minus 1 is nothing. So actually, I'll end up getting e to the x and cancel in the first term, so I get 1, plus e to the x over e to the x minus 1. Now those, again, those don't look equivalent at all. However, if I went a little further and created an LCD of e to the x here, sorry, LCD of e to the x minus 1, this first term would have to be e to the x minus 1 plus e to the x, and what do you know, e to the x plus e to the x is 2 e to the x minus 1 over e to the x minus 1. So it's always possible to make them identical. Sometimes it's actually really hard to see how these would possibly be identical, but here it worked. So go with whatever makes sense to you. Use the log laws when they help you, and if you don't have to use them, then you don't have to. So that one was a pretty cool question. Right, on to what I think is the last one. Y equals e to the power of ln x minus 2 ln x. Okay, so this is an e to the power of it. Now remember, the derivative of e to the x is e to the x, except this is the inside function, so you might need to multiply by the derivative of the inside function. Okay, so let's have a look at this. There's no log laws that I can use here, because, or is there? Is there a log law that I can use here? I just started thinking, if I look at ln x minus 2 ln x, could I not write that as ln x minus ln x squared? And could I not then write that as the quotient? Could I combine that to a quotient, which would then be ln of 1 over x? So this is entirely possible, and so that is a way to do it. I'm going to see if there's another way to do it as well, but this is entirely possible. If we did that, our question would then become y equals e to the power of ln 1 over x. I hope that makes sense to you what I did there. So let me just go through it again. I took that exponent and I kind of undid the power law and I took that back up. Reason being, if you have a log minus a log, it's the quotient of what you're logging. So you log the quotient and then that's simplified. Now why that would be cool is then the derivative of this is now e to the power of something just differentiates to e to the power of that same something, but multiplied by the derivative of the inside function. Now what's the derivative of ln 1 over x? Now the derivative of ln, I don't really want to differentiate that because I prefer to write this. So if I carry on going here, it might be easier for me to write that as that, to think about it. So the derivative of this inside function would be 1 over x, if that makes sense. And then the derivative of the inside function of the ln is the derivative of x to the minus 1, which is minus 1x to the minus 2. So let me just color coordinate there because this is a chain rule within a chain rule. So the first thing is that you are differentiating e to the power of something. Now e to the power of something is differentiated to itself multiplied by the derivative of the inside function. So this has to be the derivative of ln 1 over x. But ln 1 over x itself is a chain rule. And so if I'm thinking of that as a chain rule, 1 over whatever's inside the ln, that's the differentiation of the ln. It's 1 over whatever's inside the ln. However, what's inside the ln is still a function, and so that's the inside function of the ln. So it's almost like the green is the inside function of the e, and then this brown bit there, that's the inside function of the ln, which is quite confusing. So that looks a bit weird. So let me try and neaten that up a little bit. So this y dashed becomes e to the power of ln 1 over x times 1 over 1 over x is actually just times x then, and then it's times negative 1 over kind of x squared. So if I neaten that up some more, I'll get negative, one of the x's will cancel, so it's ln 1 over x over x. And that's probably the nicest kind of way of looking at it. Okay, now when I initially looked at this and I wasn't seeing log laws, I mean, I really hope that that log law makes sense to you, and that chain rule within a chain rule, that's quite complicated. But if I just start again, is there a different way to do it? And I think there is. It'll be interesting to see what we land up with. The derivative of e to the power of something, if I don't do a log law and I say, oh gosh, it's e to the power of something, the derivative of e to the power of something is e to the power of that exact same thing, ln x minus 2 ln x, multiplied by the derivative of the inside. Now the inside function is this exponent. Now can I differentiate that? Well, ln x differentiates to 1 over x, and minus 2 ln x will differentiate to minus 2 over x, because remember 2 is just the coefficient, so the 2 just stays, and ln x is 1 over x. So you can actually kind of write it like that if you want to. Let me write it a little bit easier to understand. The coefficient stays and ln of x is 1 over x. Now that actually was a much easier way to kind of do it. How this looks like it's not even vaguely related to each other, these two. So let's just neaten this up again. This is e to the ln x minus 2 ln x multiplied by 1 over x minus 2 over x, which actually, if I look at that, that's the same denominator, and so instead of writing it as 1 minus 2 over x, I should just write it as minus 1 over x, which again, if I neaten that up a bit, becomes e to the ln x minus 2 ln x. I'll just put the minus in front there, over x. Now the question is, and this is what you have to be so careful of when you mark from a memo, are these the same thing? The answer is absolutely they're the same thing, because look, there's the negative, there's the negative, there's the over x, there's the over x. This somehow has to become that, but it will be because of what I did on the side here. There's the exponent that we use the log law to get that, and so actually these two things are equivalent. So just be really careful when you look at a memo and they get an answer that looks nothing like your answer. They could actually be equivalent. Now, would I expect you to take this last line and make it look like that? Well, I definitely wouldn't expect that from you, because if you're doing it one way, you don't know what the other answer could possibly look like. So there's nothing wrong with leaving an answer exactly like that last orange one. So it's pretty cool how different ways you follow, you would get different answers that actually are equivalent. Now, which one do I think is easier in this case? I actually think the orange was easier. I think it was easier not to do the log law, because the log law created a chain rule within a chain rule. Now, sometimes you never know, and so you've got to try both ways, kind of scribbled and see how it's going to go. Sure, that was like a marathon. Okay, so what we're going to do now is I've made a second exercise. So now this is the end of kind of topic 3, which is the derivatives of exponentials and logs. And I've made exercise 2, which is all about derivatives of exponentials and logs. I will try in my memo to make sure that I put as many different ways as possible to do it, simply because there are so many ways. So try at exercise 2, mark it from the memo, and then please ask questions, because sometimes it's hard to see what is going on. Great, so that was quite a marathon. Really, really cool topic, and good luck with those questions.